Our third speaker is Jie Yu from North Carolina,
Yes.
and she's going to talk about waves over periodic topography. Please.
Okay. Yeah. Well, thank you. Well, first of all, I want to thank the organizers for giving me the chance to actually visit this wonderful place and actually get a chance to present this work. So I know it's a late afternoon, and actually this is going to be a very simple one. You know, this is work I started working on. It traces back to my PhD study with Changxi Mei, and then later I started pick up this idea with my friend Lou Howard, and then in 2007, then at that time we were particularly interested in the normal mode in the tank with some kind of periodic bottom. Then later I kind of extended it to a more generalized case in the sequence, in the subsequent paper. Now, the title seems very big. Sounds like I solved the whole class of problem. But, well, so to begin with, let me tell you this story. And a friend told me that, some of you probably heard about some version of it. And Willem Marcus, some of you know that, many years ago gave a talk at a conference about a linear theory on the thermal convection. And after that, there was a Russian colleague came to him and said that in Russia, only women do linear problem. So here I am. I'm a woman, okay, and and today's talk is going to be largely really just about the linear theory problem we work on. And at the end, if time allows, then I will talk about some of those nonlinear, work attempt I did. I hope it get some help or suggestion from you guys. Now, to begin with, first of all, that you already see that picture there. You can see that even though that there's not a lot of beaches really covers by there's a lot of periodic topography there, but you already see 3 cases there, right? And I just flapped through. But so what really problem is about? Now, to understand that one, that we may want to visit this the most simple problem in the waterway, which is just a linear wave and over in the constant layer of fluid over the flat bottom. And we know those problem by heart almost. We use it every day. So for the velocity potential, you have the Laplacian equation, and then you have the zero normal velocity on the bottom, and then on the free surface there, you had the kinetic and the dynamic boundary condition, and then you linearize it and approximate it as this undisturbed free surface with z equals 0. That's the definition, mathematical definition, right? And then you go and solve it using this wonderful tool, separation of variable, and then you come up with solution. And the key solution for this whole theory is that, it's actually this so-called dispersion relationship, which tells us that for any given frequency omega, and there is actually a set of a linear solution for this velocity potential, which consists of 2 propagating waves plus minus k, right? And the relationship is that omega squared equal to gk, hyperbolic tangent kh, which h is water depth. And then, so you can look at the solution is given by this, and it's sinusoidal in the x direction, and but it's monotonic in the z direction. So you can see that not only the solution is separable, but even in terms of the nature of the motion, sinusoidal versus oscillatory versus exponential, actually separate in the x and the z direction. But for that same omega frequency, you also have 2 families of evanescing wave, which exponentially decrease in the x direction and satisfy this relationship. Okay? Omega squared equal to minus kappa j and the tangent kappa jh. And now you can see that now you have exponential in the x direction, but oscillatory in the z direction. And normally that for people working in the open domain problem, you almost never care about this evanescent wave. But not so when you work in the finite domain, or wave maker problem, or the problem with beaches, or in particular, this floating body dynamics, because there's no way you can satisfy the boundary condition, generally speaking, without using those evanescent waves. All right, so having said that, so what is the problem for me, right? So the problem is that the interesting, actually it's very interesting to know that if you just slightly perturb the bottom a little bit, okay, let's say very simple sinusoidal, perturbation on the bottom, then you ask that, do we have a set of solution exact to this linear formulation, which can actually analogous to this set? So that's our problem. So here is the definition of the problem. So now we have the bottom, and so it's arbitrary periodic in terms of the shape and the height. And as far as you can identify some kind of spatial period. And so the problem is just as before, you can write down the Laplacian with the velocity potential, linearize the boundary condition on the surface there. And now the bottom boundary condition will be the normal velocity, normal to the surface at every location, okay, equal to 0. Now, one thing is that there will be always some kind of scattered wave due to the bottom, backscattering. So there's really no purely traveling wave in one direction. It's always kind of a mixture, right? And now, so here is a little bit just mathematic, a little bit description of this, the bottom. And we use epsilon b, as a relative, it's a measure of the relative, the height of the topography. So it's a crest to the trough, minimum, maximum. And so I just use epsilon b, but the epsilon b just, order 1, it need not to be small. And so you can identify a spatial period for the topography, and so therefore you define this topography wave number, okay? And now it's not necessary for the whole formulation, but it's convenient to understand the problem. So we require that this the profile, the bottom profile there, has a 0 averaging in x. So therefore we'll know what's the meaning of this mean depth h0 in the physical domain, okay? Now, and also that for the convenience of formulating the problem, we define another wave number kb, which is 1/2 of the k topography. So in the way that we want to normalize our problem such that we have pi periodic in the domain. All right, so so now in order to solve this problem, we're going to use this conformal mapping techniques. So now we have a strip of the domain, unperturbed domain, okay, and but with corrugated bottom. So we want to map it onto a uniform, constant strip, a strip with constant depth, which is h there. And now, so taking advantage of this spatial periodicity, we represent our map in this kind of Fourier series. And and also we require that the free surface z equals 0 will be mapped onto undisturbed surface eta equal to 0. And then another condition is that we want to stretch our bottom flat. That's the whole purpose of this conformal mapping. So as a result of that, as a result of mapping this, so as a result of mapping this to this, which is here, and then you can actually, by iteration, determine what's the coefficients of this BG and CG. Okay, so it's an iterative method in place it. And also that because we represent our function, so we actually preserve the spatial periodicity. So it's periodic here and also periodic here. Then the price you pay here is that then the actual water depth in the mapped domain is no longer, it's not, you cannot preserve this mean water depth. It will be reduced to that. But later it turns out that the actual depth in the mapped domain really tells you a lot about the dynamic of the problem. And as the corrugation becomes to be very high, okay, just if you keep on increasing the the height of the corrugation, then eventually find out that this mean water depth H0 in the physical domain really lose meaning. It doesn't really tell you the whole story. All right. Now it's just mathematics. You transfer your equation boundary condition into this matter domain, and now because the problem right now is linear, and you can see that the only complication right now of the transformation is this free surface boundary condition. But the good thing is that it's still expressed as this undisturbed surface there because it's a linear, right? And the sigma right now is a normalized frequency in this way. Okay. All right. So now we look for naturally because of this periodic coefficients in the free surface boundary condition. So we look for a flow K kind of solution. So it's this flow K exponent mu and then multiplied by this periodic factor. Now this periodic factor is written down in this kind of Fourier series way. And but the one thing you notice is that the individual term in this sum here, this is not a separation of solution because the individual term here satisfies Laplacian, satisfies the bottom boundary condition, but it doesn't satisfy the free surface condition individually. It is whole sum together satisfy that condition. And as a result of that, you got this recurrence formula, link all those coefficient dn together with this coefficient theta represented here, which is purely come from the mapping. Therefore, it's purely related to the geometry of the problem. Okay, and also that even though the solution is written down in this kind of form, but when you actually start looking for the solution, then you can find out that for any given frequency, okay, you can actually determine a set of this mu, flow K exponent mu. And so that set of flow K mu consists of two, we call it propagating wave mode, but it's really a wave mode, okay? And which plus minus mu. And this mu can be either real or pure imaginary, depends on the frequency. But on the other hand, you also have two families of mu, which are actually corresponding to the evanescing wave in the flat bottom, okay? We claim that this is a whole set, but honestly speaking, we don't have mathematical proof. The way we know is that by looking at this asymptotic limit, when we take this as solution, we gradually reduce our bottom to flat. Then we can see that these two modes, okay, will reduce to the either propagating wave mode or a standing wave corresponding to that frequency. And these two families will reduce to the set of evanescing wave for the flat bottom for exactly that same frequency. So this is how we know that this is a set of solution, okay? But yet still we don't have proof. But the indirect proof is that we can actually use this set to construct the linear boundary value problem just in the way as you would do for those set of solutions of the flat mode, okay? Now, so the crux of this whole problem right now is to determine this relationship between the frequency and this set of flow K exponent. So that relationship is what we call this dispersion relationship. And from this recurrence formula, so you write down this matrix form, and obviously that for non-trivial solution, and this determinant of this matrix has to be equal to 0. So that's this dispersion relationship here. And so this equation is infinite, okay, because that unless you truncate it. So it's kind of like similar to this Hughes infinite determinant there. And once you determine this the relationship between the frequency and the flow K exponent, and then the solution for this those coefficient D to close your problem, then that is given by the vector in the null space of this. Okay. Any questions? I know it's simple. Okay, now here, what?
I have a question. Can you say something about the convergence of the bi-infinite determinant?
You mean this one there?
I mean, Whittaker and Watson go through quite an elaborate scheme to make sure that they have a convergent setup.
Well, first of all, is that this those coefficients, right? They decrease very rapidly because they related to the flow, the Fourier coefficients of that, of those the representation. And you know that even though when the unsmooth function, the Fourier series converge there. And another thing that we are not actually solving the eigenvalue of this matrix. We only want the determinant. So I checked that, actually that Jeffrey and Jeffries made the remark that for the Hughes, infinite determinant, you can always scale your, doing the row and the column scaling and by factoring out and then find the zero. Find the zero with this determinant equals zero. And
this is normal derivative operators in one dimension. Therefore, each kernel is logarithmic kernel, like integral operator. For such, each is integrable. Therefore, it is solved for a kernel operator with kernel. And for this operator, determinant exists and converges. In 3D case, it is not really solved, but in one-dimensional case,
only for finding this zero. Okay, so it's not but for the eigenvalue of this whole thing. All right, so here's one example there, and now, so this is a doubly sinusoidal bottom, and it's actually used by in existing experiments, and you can see that it's very large bottom because anti-surf free surface over there. Okay, so we'll touch you there. And the solid line of the profile, the dotted line here, just shows that what function look like when you plot it, once you find the map and plot it in the math variable. There's actually another curve coincide with solid line, dotted, you hardly can see. That is actually inverse of the map. So in the way that tells you that how accurate we actually find the map by this iteration method there. And so now that for the wave mode, the so-called wave mode, that's most interest, right? So for those wave mode on this parameter domain, which is frequency, and versus this correlation amplitude, okay, and those so-called wave mode are actually separated by those isolated bands, okay, or the resonant tone, in those.
So I'm a bit confused about the dotted line there.
Yeah.
So you're saying one is versus x, one is versus psi. So those are the conjugate variables, right?
Okay, now those dash curve, okay,
Yeah.
is that I plot this function as a function of this variable c, okay, and.
But that would mean that the map between x and c looks like it's got some singularities.
No, it's not. It's that, actually on the map domain, right, you don't even, so this is a curve you would see when you plot it at the bottom there, but you don't have the singularity when you move up to the surface there because the curve is being constantly stretched.
But since your bottom is so smooth, why is there even a singularity? I mean, I can see if you have corners on your topography,
Yes,
you
yes.
get singularities
Yes.
on the bottom, but for
Yes.
a smooth curve, the
Yes.
conformal map is smooth
Well,
at the bottom boundary.
actually, I think I heard some remark about this kind of conformal mapping is always flatten the crest and then peaky the trough there. So that's how you see there. But on the other hand,
that's
this,
different from what you have there, though, I think.
no, it's not. But by the way, this. Okay, fine.
People are fighting.
Now, first of all, is that this function itself, okay, this function itself does not even come into your formulation because the mapping coefficient really shows up the free surface there.
Maybe you
So-
shouldn't have plotted it.
Yeah.
What? Yes, I should. And so here it's just that I take this function, I just plot it as this, in the way that I plot this one. Now I'm going to evaluate for any given x, I'm going to evaluate this conceit, I'm going to replot this function. That's all. Okay?
It might be just distorted because you plotted them both on the same picture. You plotted it just versus
No.
C over here and just versus X over here. It might
No,
be
it's
fine.
not quite right. The way I think about it is that I stretch the curve, right? But I still want to maintain my periodicity. That means that my pi distance is still same pi distance in the map domain. So therefore, that while I'm stretching my, one part of it, I must squash the other part.
Yeah.
So therefore, right now is that you can see that the result that you actually you stretching the crest, but you have to squash the bottom. So that's how you understand this, how the mapping actually works there in a way. Right? Satisfies you?
Okay.
Okay, good. All right. So those isolated towns there. For this one, just forget this dotted curve. Just look at this and this. So those isolated towns we call the it's called a resonant town. So we said that for any given corrugation height, okay. Now, if the frequency is within this wedge here, then there's no spatially periodic solution because flow K exponent mu is real. Therefore, that the solution, any kind of sinusoidally, a wave going to exponentially decrease in one direction or the other. And then it depends on the frequency. When you go higher, you have this, the M equal to 1 resonant town and 2, 3. So those ones corresponding to this, the M's or the Bragg resonance in the solid there, okay? Now, so at the wedges of those towns there, then you can see the spatial periodicity of the motion is corresponding to this relationship, okay? And the mu equals 0, so therefore you can expect exactly spatially periodic solution right at these wedges there. But outside this wedge, flow K exponent mu is pure imaginary, therefore that the wave is actually spatially modulating, okay? Yeah. And then we can actually calculate the actual flow K exponent mu given, given the parameter of corrugation height, which is, those value there. And just skip the detail. Now, to look at how the solution look like, so now we pick up certain value. Let's say that if you pick up 2 points here, here, and here, then I can see what's the solution phi velocity potential look like, and also those higher ones there. So that's what you're saying here. For example, those two corresponding to 2 points on the left and the right wedge. So you can see this is what the solution look like, the periodic factor look like. Evaluate the free surface. So therefore, this is actually the free surface you're going to see within 2 pi period. And the two curves, the solid curve is actually function, which is x. The other one is again plotted in the mapped variable. Okay, and so this is the point on the left of the wedge for M equal 2 resonance. Now, in both those cases there, you can see that if we define the so-called wavelength as the horizontal distance from one crest to another crest, or one trough to another trough, right? Then you can see that when you move on to the higher frequency, okay, so M equal to 3 and 4, and the mu equals 0, so therefore the motion is spatially periodic, and we can identify spatial period. But however, right now, if you look at horizontal distance between any two crests there, their distance becomes to be smaller than the spacing of the corrugation. Therefore, that you can see that this crest and this crest are not exactly repeating. But you said after 2 of them is repeating with another one. So the motion itself, in this case, is 2 pi periodic. But if you look at the so-called wave crest, it's not exactly repeating between this distance, because this distance right now is smaller than the periodicity pi of the problem. And same thing here, that you can see that this every other one is repeating. So the motion is pi periodic, but the crest itself is not repeating, but every other one. So in other words, that if you define those called wave by identifying crest to crest, there isn't such kind of spatial periodic wave with a wavelength defined by the horizontal distance crest to crest, which is smaller than the spatial periodicity of the problem allows. In this case, it's pi. Okay, so now here just showing that for the same frequency, if we calculate this, not frequency, if I pick up a frequency, then I can calculate the first 3 evanescing modes. And those are the solution given by this flow K theory. You can see the very large number, so therefore the solution decrease in X very rapidly. And we also compare with the eigenvalue come from the flat bottom theory. You use that dispersion relationship. Now there you can either use that function, omega squared equal to minus tangent kh, But now you can have decide whether you want to use this mean water depth in the physical domain or you use this water depth in the mapped domain. Because when you do naively thinking, if you want to work on this kind of problem, you always think about that the mean water depth in the physical domain will tell you something, right? So even though when you're making your amplitude is getting bigger and bigger, so now here you can see this flat one is for this. Yeah, you can see that this is a calculation using the depth in the mapped domain. And you can see that they're actually fairly close to the flow case solution. But if you use the mean water depth in the physical domain, you can see how far it's actually off. So that's interesting that you can keep the same mean water depth in the physical domain, then you just make your crest, bottom crest getting higher and higher, top getting lower and lower. You got a big, corrugation. And but then when you reach to that stage, this so-called mean water depth really loses meaning. When you think about it, it makes sense because your wave is on the surface there. It actually fills the crest more effectively than this deep valley down there. So this is one thing I thought is very interesting because this kind of mapping actually can explicitly let you to see what is that effective water depth. You can see actually that this resonant tongue, which is sweeping towards this low frequency you see in the previous slides, is also due to this effective depth is reducing when the corrugation amplitude is increasing.
So,
What?
can you find a relation between the say the envelope H and H0? I mean, it must
Oh, you mean
depend-
this H and
Yeah,
this?
it
Oh,
must
yes,
be-
we
it
do.
depends on the variance of the bottom. Yeah.
Yes, we do. That's part of the mapping. There is a there's a relation between this, and it also depends on the height of the corrugation and the shape, of course. Yeah. So that's part of the mapping. All come out together.
Yeah, sure.
Yeah.
In homogenization theory, where people have a rapidly varying material parameter,
Yeah.
which would here be the depth, it's also known that you don't take the mean of that parameter, but some other, not a standard mean, but another mean. So this is from that context, it's not surprising that you don't take the standard mean, but another one.
Yeah, if you look at the stuff, I mean, Andre Nakben has worked a lot on conformal maps for 2D waves
Yeah,
and
I saw-
random topography,
Yes.
right?
I saw his talk.
And essentially, he has a formula that tells you which level the effectively the wave is seeing, right? And it's always above the
Yeah.
topography.
Yeah.
Yeah.
Actually, 2 years ago, I heard he gave a talk. At that time, he was actually guessing. What is that
Well,
water
no,
depth he had to have. But right now, he
So
probably
recently he did the Benjamin Fearon stability,
Good.
and you can stabilize Benjamin Fearon deeper water by putting the topography that comes up because your effective KH is a lot smaller.
yeah.
Because
Right.
when you look at the diffusion equation with random topography, it's actually the inverse of the mean of the inverse. That's actually the parameter, not the mean of the parameter. So that's a nice result. In John Hinch's book, he actually explains how to get it with perturbation.
But anyway, just for us that we have an explicit formula between those two. So that's all.
I think it's the mean of the Jacobian of the conformal map, or 1 over the mean of the Jacobian.
Yeah, it's a different case, but it's something.
I think it's variance. Because I can tell you, in metrology we use concept of envelope orography to measure, to measure the effect of fluctuations in the mountains.
Well, just another example. I tried quite a few other examples there. So here's another one, basically just blog. So I rounded the corner a little bit just for the computing efficiency. And then here's those resonant tongue for this wave mode, dispersion relationship. But the interesting is this one there. And you can see the resonant tongue, actually the two boundaries merging at one point and then open out together as you keep on increasing the corrugation height. And when I gave this talk last year at Woods Hole, and some people may comment that in the crystal physics. So when it comes to this one, that's usually indicating that there's some defect in the medium. Then I said, what's the defect in my bottom? I don't really understand this one. So it's just how the computation come out. Okay, yeah. Anyhow, so so far you can see that actually the theory has no restriction to the frequency. It works for all the frequency you can calculate it. But however, that for periodic wave in the periodic medium, right, one of the interesting phenomena is this so-called Bragg resonance, and obviously that the name comes from this crystal, X-ray physics there, and so we said, okay, now first thing we just try to use this theory, work on some of those Bragg resonance problems there, and so Bragg, right, the name says that, it means that it's associated with two Braggs. But when I was working on this problem, and I found this passage from Riley's work back to the 1987, and said that perhaps the simplest case of the kind is a stretched stream, periodically loaded, and propagating transverse vibration. When we imagine that the simplest small loads to be dispersed at equal intervals, if the wavelength of the train of the propagated wave to be approximately equal to the double interval between the loads, then the partial refraction from the various loads all occur in phase, and the results must be a powerful reflection, even though the effect of the individual load may be insignificant. And that's precisely what Bragg resonance happened, is that when the light is shining into a layer of crystal, right, if the spacing between the layers and forming this relationship with wavelengths, then you can achieve strong reflection. And the same thing with water wave. When the wave passing through those corrugations there, each of the crests may reflect a little bit away, but if the successive reflection, right, if those crests are spaced within a certain relationship with the wave, then those successive reflections all in phase, then you add up with stronger reflection on this end. But the interesting thing that, look at the date here, that is 3 years before the William Lawrence Bragg was born. So next time when you try to do something, check out what he has to say. So, all right, so the first example here is that this is a very well-known example in coastal engineering study, because this idea about that you can achieve strong reflection, through the backward scattering. So obviously then the energy carried by the wave should be decreasing towards shoreline, right? If you can achieve that, wonderful, then you protect the beach because you have a smaller wave come in. So for that reason, that back to this time there's a lot of interest in coastal engineering. So here's one experimental setup. So you had a wave coming in, and then there's a corrugated bottom. Then you had a beach here to observe whatever transmitted. And then you try to measure the reflection coefficient at upper wave end there. You can also measure the wave height crossing this corrugation field as a way, then you can calculate the energy, density distribution. And this example has been used by many, to compare with theoretical, studies there, but mostly concentrate on those data for smaller corrugations. And here I dig out the original report, and then I found out those three cases which really had a relatively larger corrugation, amplitude. And for those cases, I know that so far only being compared by the numerical simulations, even though you solve linear wave, but still this one becomes very large. So what's plotting here, the dotted line there, with the dots there is the data, actually measure the amplitude of the oscillation. So here is the largest oscillation and the minimum. So it's anti-node node or envelope maximum minimum. And so the solid line are our theory. So you can see that, we matched very well. And but if you look at this, even though for this very large one, you can see that we compared very well there. But if you actually do the numerical, solution of this one there, one of the methods people use is just discretize your domain into those steps. And now each steps, what you do, so you use those the set of mode given by the flat bottom, then you end up with many those constant depth problem. You have to patch them up, and so it becomes to be very numerically extensive, even though the problem is linear. But right now for us, we have no problem because the mode we gave are satisfied for this kind of bottom. So all we need to do is just find out the linear combination by satisfying the boundary condition at the end there. So, and so we can also try with just, for some kind of bottom here, and you can try to play with different parameters and try to find out what kind of solution you can have. And this is done by one of my student there. And so in this case there, the previous result, you see that the wave, once you transmit it, you just let it go and never come back. So now you ask the question that what would happen that if the wave will be reflected, say down at the beach there, and come back, then they will also get it back scattered. So what is the ultimate solution? And so now you can see that depends on the magnitude of this reflection back from the beach, and also depends on that how that wave, what's the phase of that wave when they arrive at this age here. Then you could access a solution which is not monotonic decreasing, but rather decrease and then increase. Okay? And you can also find a solution actually instead of monotonic decreasing towards the shore, it's actually increasing towards the shore. So in this case, that the corrugation itself kind of forming a medium and just constantly draw the energy from the big wave maker down at offshore there, and trap the energy at the shoreline here, unless there's some other magnetic take up, such as breaking. And in fact, this was when I was working with Ceci on my thesis. I found this solution, and I got a whole lot of hard time because nobody believed this solution. Because they all believed that the Bragg scattering should decrease the wave energy towards shore. But that is indeed the case if the wave just go pass by, never come back. But not so when you do have some amount of reflection at this end there. So now we use a different solution. We show that actually is actually the case. And this is another experiment. This one is a little bit busy. I think I'm going to skip that one.
So how sensitive is that to the incoming wave, whether it is going to amplify or decay?
That one does not depend on the incoming wave, but really depends on how this wave, this short reflected wave, how that one, what's the magnitude of the reflection and the phase of that wave when they arrive at this age, so incoming wave here, the phase of that wave relative to the corrugation. So it's really determined by that. So that's what we find out.
This is linear problem. So if
Yeah, this whole thing is
if
linear.
I have a random wave field coming,
Exactly.
so what will be the outcome? So
That
what
was
is
my
the
question.
Yeah, but
Then you just-
in question, you don't have a random wave field. You just have waves coming in.
Yes.
And they have a determined phase. If you
Yeah.
have a
Yeah.
reflection with the right phase relation back, then boom.
Everything is linear. So if you do have a random wave coming in, right, and then you can try to just think about that one as many linear waves adding together, work out the individual rather than work out spectrum, right? Because right now it's linear. But what's going to happen if you include the nonlinearity wave interaction? I don't know.
But what now if you don't have random waves with a wave spectrum? Ask Peter for
yeah.
a good wave spectrum.
That's right.
and
Well, that's why I'm
realistic.
presenting this
Yeah, yeah.
problem.
What
So
happens then?
No, but yeah, but there are two parts of the equation of the world, When we talk about ensemble and spectra and random phase, basically we are talking about an ensemble of
Yeah.
Earths, not one Earth, n Earths. And then, we throw in phases and then we look at the ensemble average. But of course in nature, if a wave is coming, it has no random phase, it's not picking every time step another phase, so it's just having the same phase.
Well, I
So
didn't
that will
ask
be-
you the question. When
that
you
will
have realistic wave field coming in over your corrugated surface, can you then make a wave pump? Because it's essentially
I
We
don't
can
know.
play.
I
You don't
haven't
know.
tried that yet. And also I think that it depends on how you do that, right? If you're trying to transform the spectrum itself, that's one story. Or if you want to think about just wave by wave individually, that's another story, right? Yeah. And so I don't really know. Depends on how you do it. Anyway, I'm going to skip this example. It's just experiments we compared, and then it turns out to be work very well. But I want to show this experiment because those the wave spatial variation of the wave can be decreasing or increasing, increase if you have some reflection. So that inspired me to think about the normal mode standing oscillation in a tank. In that case, that you basically have a standing wave back and forth, right? So therefore, that if my theory is correct, then by changing the position of the end wall relative to the corrugation, then I should be able to identify those different trends once I tune into the Bragg resonant frequency. So when I was giving this talk a couple of years ago, and Patrick Whiteman was there, and then he happened to know how to exciting standing wave in the tank. He said he wanted to do this. I said fine. So we have this 5 meter long tank. Then we put some corrugation in it. Okay, roughly about 9 of them. So this is 2 sections. And then at this end, it's connected to a motor. So we're just oscillating this plate. So the whole tank is very slowly, oscillating. But we had to tune to that frequency. And then you excite the standing wave. And now, if we can adjust the end wall position relative to corrugation there, then we can predict that whether this Bragg resonant standing oscillation, okay, will be exponentially decreasing from this end of the tank to this end, or from this end to that end, or you could have a symmetrical case which is larger oscillation at this end, minimum in the middle. For those of you who know about the standing oscillation in the tank, you know that. So you begin with antinode at the wall, node, antinode, node, antinode, and the number of that depends on which normal mode you're trying to excite, right? But the oscillation at all those antinodes there should be identical if the tank is flat bottom. But now we put into this corrugation. It's not very big. It's the height is 5 centimeter, and the water depth goes from like 14 centimeter to 8 centimeter. And so here shows one case here. So this is actually the dot here that actually the surface elevation at the instantaneous time over this distant length here, the solid line calculation with different time. So this is the entire tank, okay? Now this case, we set up that the theory predict that if you make the end wall here relative to the corrugation in such a way, then you can see the oscillation should be exponentially decreasing this way. And here's a comparison with that. And it's very, it's very noticeable, change, because it's only within one wavelength distance, you already see the exponential decrease. Then the second case here, what we did is that we just moved this end of the wall inwards by 1/4 of the wavelength, corrugation wavelength, such that we had a symmetrical case. The corrugation on the bottom is about 52 centimeters, so the distance we moved is about like just 12 centimeters, versus a 5 meter tank. And now in this case, you can see that it's a large oscillation this end, large oscillation, but minimal oscillation here. The whole thing has nothing to do with nonlinearity. It's purely linear. Yeah.
I don't understand those separate curves. Could you explain what?
Oh, those are just a different time. At a different time, the exact, the surface elevation.
It's a standing wave at different times.
Yeah, the surface. Yeah.
So now you refer to this as linear, but it's actually the theory that's linear. The fluid is probably nonlinear.
Well, we make our wave, just very, very small, as small as possible. And we do see the nonlinear effect from our measurement, for example, from the time signal, right? You can see that when the water depth getting very shallow, and you have those peaky, cracks and the flat trough. So that's indicating that the Stokes wave is kicking in, yeah. Okay, and another thing try to show is that, if you try to solve this normal mode in this kind of tank, right, you really need those evanescing mode in order to satisfy low flux boundary condition, this wall there. And, for the ordinary rectangular tank, we know that by luck, we only need the 2 propagating wave. We can satisfy the boundary condition there. We don't even need evanescing wave. But when you have the corrugated bottom, right? So the wall, even though it is vertical here, but it's not so relative to corrugation. in the mapped plan, you can see that the vertical wall here is actually a curve. So that tells you that you always need evanescent wave. So that's what our flow-K evanescent wave come in. So we can use that. So here you can see that this is so U should be equal to 0, normal velocity at one end of the tank. And when we only use like, I think it's a 3 evanescent wave, this is how the results I got. So I pretty much satisfied except toward bottom there. But if you only use the 2 wave mode without using evanescent wave, you can see that this is what actually the normal velocity calculated that wall there. So it's really, in the average sense, you satisfy that boundary condition, but you did not truly find your solution unless you use those evanescent wave. Okay, and this is just quickly show some other interesting that if you try to excite the normal mode for even higher frequency in that similar tank. So here we have 16 corrugations there, and so now you can see that you have this exponential modulation. But right now, this comes to this case I'm talking about, that you can see that the wave crest, the crest and crest do not repeating, but every other of them. So you have this long range modulation and also a short range modulation within the range of this the spatial periodicity at the bottom. So just some curiosity, may not be really interest anyway. So do I still have time on this? I'll just go quickly about this because I think something fishy there. But but naturally that you want to do something, nonlinear waves, so on and so forth, right? So you can just try to follow the standard procedure, doing the weakly nonlinear analysis, but now everything in the mapped plan. So you can write down those equations. It's messy, but we know that. And now here the question is that you saw those flow-K solution, right? It's represented in those Fourier series term with those coefficient dn or some, those. And those dn's are actually a vector, element of a vector in this null space of that matrix, determine the dispersion relation. So now you ask the question is that if you do the weakly nonlinear analysis, so how are you going to do it and what you're going to allow? Okay, now to see that, one thing I want to say that for the typical flat bottom case, if you have a wave which is, because this is what you generally write down. So this is leading order, you have this wave. And if the wave is modulating with a group or something, so this is at the leading order. And the second order, you know that you're going to get this equation. If this is time, you define some small, which is parameter, which is amplitude. You have those T1 and then x squared T and x1, x, blah, 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 right, standard. And then you got this equation, right? And then once you go to this, the third order, and then you got this nonlinear Schrödinger equation for this. Okay, that's all standard, right? So now for the flow-K solution, I have something like this, and times this periodical factor, okay? Now, then this guy there, I have the sum of those dn, blah, blah, blah. So now, the question here I'm asking is, okay, should I try to follow this kind of standard way, but thinking about that, I just have one constant represent the magnitude, then I'm trying to find the equation of that, or should I think that those coefficient dn's there, okay, they are actually can be separately modulating in the longer time and longer space, but yet not arbitrary, and they are bounded by some relationship. So what I was, so my first approach was trying to think about that those coefficient dn are not absolute constant, but they are actually individual components are actually changing. So so I just started doing that, and I have to go too quickly. But what I want to show is that if I do that, I end up with this whole set of equations for each of those dn's in terms of slow time and slow x. And if I write down in the vector form, I got this equation. Now this equation is fairly similar to this one you're seeing there, except right now I have a matrix here inside the group velocity. And so it's the eigenvalue of this matrix actually plays the role of this group velocity. And I can see at the limiting case, right, indeed, the largest eigenvalue of this matrix A really goes to this CG. So, but on the other hand, I have to difficult to understand this kind of result. And not only that, if I just carry on, it's very messy. But if you just carry on, at the second order, you get another matrix equation. And the one term there, you can actually see that it kind of really like a placeholder corresponding to the typical, nonlinear Schrodinger equation, except that right now the coefficients are all written in terms of the matrix. And in fact so if you can simultaneously diagonalize the matrix here and the matrix represented here, then, so this is group velocity in place, or here is actually the second derivative, d omega dk squared. But the question is that can you actually do that? Yeah.
You also did mean flow.
Yes,
Yeah.
yes. The mean flow part actually identical with this flat bottom case. The equation for that one. But for those ones there, everything becomes to be a matrix form, vector form. It's really amazed me in the sense. And not only that, it depends on the frequency, whether inside the resonant band or outside the resonant band. And the eigenvalue of this matrix actually is not always real. When that one is not always real, you cannot even call this a Schrodinger equation. You cannot even call the previous equation is a wave equation because it would be elliptic. So that's why I think something's wrong. So maybe I should think about that. Just you have one of that, and then find the equation on that. But in that case, that you would think about that the interrelationship between different dn's coefficient will maintain fixed. So I don't know. That's actually one of the things I saw that maybe you guys can help. Now I'm putting on my engineering hat. So all right. So I think since I put it there, just recently I saw that I took the interest about this mapping techniques, and I actually applied it to study this the viscous fluid, but it's boundary layer. Kind of trying to study some terrain following boundary layer flow. And one example is actually in a very narrow channel. If you're vertically vibrating the channel, and through nonlinearity, you can rectify that motion into a steady flow in the horizontal direction. And the spatial asymmetry actually can break this the pumping direction, and then transfer the fluid from one end to another end. So it was very interesting thing. I want to see how this conformal mapping works when you have to study this, the viscous fluid, because the equation becomes very messy, and also how to determine the pressures that's involved in this problem. But anyway, that's just a little side story. So, so here's a quick summary there. I think, I don't know. I guess I already said most of them. I just leave it there, and for you to read it. And in the meanwhile, I answer questions.
I think you shouldn't be hoping to find NLS. You should be hoping to find Davy Stewart's then, because you're not in deep water. You're in fairly shallow water.
No, it's not naturally shallow.
Yes.
It's not naturally. It's finite depths. You can see.
Yeah.
Yeah, but it's Davy Stewart's.
It's Benny. Benny.
Sort of.
It's a more Benny equation because David Sturgeon is long-term limit.
So
Yeah, right now.
2D.
It's a 2D.
2D.
Yeah.
But the first term that you were concerned with,
Yeah.
right? That's a linear term.
Which one? You mean that you back to this?
Yeah, the two terms that you're worried about,
Yeah.
M11 and the next thing, those are all linear theory,
Yes, up to here is linear.
right?
So the first part here is linear. Yes. Yes.
So somehow, I mean, I don't claim to have an answer, but the way to look at that is to just I don't think to look at an NLS, but just to look at the Floquet modes themselves.
Yeah.
I mean, that's what.
But that's what you're doing, right?
Well, you see that if you look at Floquet modes itself, then this is what I'm trying to say. Whether you think about this whole mode just characterized by one unknown constant, which you're going to determine the slow modulation in terms of this way, or you think that, because this coefficient itself, right, is related with the frequency. So the modulation means that you have a group, so the frequency is actually kind of like, a narrow band or something, right? So therefore that when the wave is modulating, whether the individual, the coefficient dn should change slightly by following certain rule. So that so-called change slowly following certain rule is actually determined by this matrix there. So it's a different way of looking at things. Right now, quite frankly speaking, I don't know which way to look at it. Now for this one here, right, formally the equation look like this nonlinear Schrodinger equation. That only provides that you can simultaneously diagonalize this matrix and the matrix here. And not only that, the eigenvalue, the eigenvalue of this matrix here has to be real in order to be this equation to be called NLS. Otherwise, it's not. I don't know.
There's a complete theory about this problem for in nonlinear optics. If you do nonlinear optics in photonic crystals,
Yeah.
you have a system, and it's well known how to derive NLS on these equations for this kind of system. And I think it transfers one-to-one to the situation here.
Okay, I answered the question. I got some suggestions similar to that, and I looked for some of the references. And so far, the one I look at it, I'm pretty sure that there's a lot of things I don't know. And so far, the one I look at that they have already have those coefficients, like either same constant or is already at diagonalized. So therefore, that the structure of the equation is pretty clear, even though the unknown is written as a vector. But right now, for me, that those are the four matrices, and then those are the four matrices. I need to, diagonalize them or look at their eigenvalue. So that's part I don't know. So maybe if you have some other reference, I like to look at it. Yeah, Javi?
Yeah, so another issue is, nonlinear Schrodinger is a narrow wave band approximation.
Yeah.
You could think of your corrugated bottom as being a second wave packet. So it's really not propagating on its own. The packet you're looking at is not really propagating on its own. It's propagating in the midst of another wave packet, which it happens to be fixed on the bottom.
Well, if I want to think of my bottom as a wave, then that's a zero frequency wave, right? Because
Well, it's not moving, but
not moving, so therefore zero frequency. Yes.
well, you could think of a short wavelength wave packet running, interacting with a very long wavelength wave packet, and then the speeds are so different that it's almost like what you're talking about. So I don't think you can just dismiss that.
Yeah. That would be like a approximation at a certain end or limit or something, right? Yeah. I haven't done that. Right now I just take general just arbitrary depths and then
Right, but
arbitrary.
you're only considering one wavelength, basically. That's not necessarily what you should be doing, given the situation you're looking at.
Or rather say that my leading of the wave is really it's a group, but characterized by this central frequency. Yeah.
Any further questions?
Behind you.
There was one.
Clarify, so in your analysis, what are the boundary conditions on the free surface?
What?
The boundary conditions on the free surface.
Just the same thing I already use, the free surface, right? Yeah, I have this kinematic boundary condition and the Bernoulli equation applied at the
So
free
it's the
surface.
ladder boundary.
Oh no! Right now the theory itself do not impose any kind of lighter boundary condition unless I make application such as this the tank. Yeah. So the theory, the flow case theory right now for that linear problem is formulated for indefinite domain.
But in your results, so what boundary conditions? Show some plots. You have to do some
That is one period of the plot.
So it's periodic,
The bottom is the periodic.
and so no boundary condition on the free surface.
No, just like the ordinary flat bottom case, you don't have any lateral boundary condition unless you look at any specific problem. Yeah. So, I don't know. Maybe I missed something.
Things, if you go back a couple of slides where
Which one?
Yes, that.
Yeah.
I just wanted to have another look at it. Thank you.
Okay. Yeah. In a way that there's no lateral bounding condition right now imposing, and for the linear problem, you just chalk out all those nonlinear terms.
I guess that's why you can include both evanescent and propagating mode in your formulation, right? Specifying in the bound function.
Yeah.
Okay,
Yeah.
talk
Ah,
about it.
sorry.
So psi goes from 0 to 2 pi, the horizontal coordinate. Is that right in the problem?
Was bottom space? I mean, for the bottom, okay, is pi periodic. But however, that your motion itself, even at the linear, is not necessary to be spatially periodic. It depends on the frequency. Depends on whether your frequency is in the forbidden band or is not. So we do not assume that our solution is spatially periodic. We do assume that we have time periodic solution.
Right, so in the top line,
Yeah.
you've got a limit on the vertical coordinate, eta.
Yeah, that's right.
And
Yeah.
you have no limits on psi.
No.
Okay, thank you.
No. Yeah.
But when you solve the Laplace equation, you have to specify bound conditions. You get evanescent propagating.
No, we didn't do that when we do the flat bottom case.
Any further questions? No, then thanks to
All
you
right.
and to all our speakers.
Thank you.